Okay, Mars Homestead Project, a mission to design, fund, build, and operate the first permanent settlement in space, and we chose Mars because it has all the volatiles needed. So, outline of the talk, a little bit about Mars, but I'll go through that very quickly. The vision of the settlement, the resources, and this is an ongoing project, and we can use help from anybody in the room. Every single one of you has a skill that can help us get into space. So, self-sufficiency is the key. The reason it's the key is you want to be able to survive a funding cycle. If you have a permanent base on the moon, and there is a cut in funding, it's too easy for the people to come home. If you have a permanent base on Mars and you have a 2-year launch window before you're even capable of coming home, and you have enough consumables in case your launch vehicle didn't work so that you can survive another launch window, if you can survive 4 years because of the launch window problems, then you can survive a funding downturn. So it's very simple. A lot of people don't explain it that way. I'm not saying the moon is a bad place. I'm not saying the asteroids, low Earth orbits are bad places. They're great places for tourism, for testing equipment, for harvesting resources. Someday there will be a thriving trade between asteroids that have different resources. But a good first place is where you have the nitrogen, carbon, and water, and where you're planning to survive long enough to survive a funding cycle. Let me just keep going. So we had what we called a programming study, a design study, and we tried to figure out what materials could be manufactured on the surface of Mars to construct a permanent base. And this is the results, courtesy. A lot of these diagrams were made by Georgi Petrov, who was an MIT student in Masters of Architecture. He's now an architect and civil engineer in Texas. Let's see. You will notice it's built into the side of a hillside. We chose a hillside location for this base partly because one reason for this initial base, besides getting a foothold, is scientific research. So you have this hillside here where you can climb up and do geologic work, and you're in the middle of a canyon. So here's the map of Mars showing elevation. Do I have a cursor? Yeah, I do. So this whole region over here was pushed up somehow and presumably split open. And this is a good way that we can see ancient sediments, lava flows, dust deposits, whatever. At least, if we're going to see them anywhere, it'll be here. We also have some interesting volcanoes. For those who is not familiar with the geology of Mars, or with the terrain of Mars? Wow, that's great. Okay, let me just remind you, you have the flat northern, dusty, you have polar caps. There's a lower basin here that's very, very low. The atmospheric pressure is actually much higher. That might be a reason to relocate the base to either where it's easier to build or higher pressure, or maybe a polar cap. But for now, we chose Candor Chasm. And zooming way in, I skipped a bunch of slides here. Here's our little teeny tiny settlement down here, and a few kilometers away are nice flat areas where you could land spacecraft without overflying the base. And zooming, by the way, these bluffs are about 75 meters high. The sand dunes are fairly low. You can probably drive right over them. You can certainly drive along the edges of them. You can explore this valley, get up out of the valley, and go quite a ways. So this would be the initial base where you not only learn to live, but then manufacture stuff that you can go out beyond here. And by the way, you would have transponders on many of these hilltops for local navigation. We were comparing to the NASA Design Reference Mission, which is not that dissimilar from the Mars Direct plan. We are assuming that somebody else designs interplanetary craft and the some kind of habitat you can live in. These are the so-called tuna can habs from the NASA Design Reference Mission. So we concentrated on just beyond that. We would have increasing numbers of people, 4, 8, and 12 people arriving, living in these temporary quarters, doing the construction. So here are these tuna habs and the experimental greenhouses brought from Earth. And so they're living up here, and they would deploy manufacturing equipment. Initially, gas production to extract oxygen, breathing gases, nitrogen, argon, and either we hope to drill for water and nuclear power plants, and this initial manufacturing area, including right here, is a very large module, big enough that you can, inside it, you can build other modules. You see these 3 dotted circles are the same size as most of the other modules. And then there's an airlock on the back. So we are actually manufacturing indoors, taking it outdoors, and adding to the base. This base will grow around the hillside. You see greenhouses, private living quarters, basically bedrooms, bathrooms, garage for repairing rovers, workshops, the agricultural processing and waste processing, common space laboratories. Here is a 2-story high area that you can grow tall crops in, such as bamboo. Right, my mouse is on a short tail. There we go. Okay, so you manufacture standard size modules. I'll get to the materials later. I think fiberglass. And the construction method that we chose was some of the modules will be out on the flat area and covered with regolith, such as this is an opaque greenhouse. But for a lot of the habitats, we would dig into the hillside as far as we could safely into the scree slope, and then build masonry structures, because masonry is fairly cheap to make, and we're not too concerned about quality control, unlike, say, a sheet of aluminum. Line it with plastic, some plastic liners on the outside, and cover it with enough dirt, regolith, that it can hold the air pressure. These are skylights piping light down, and here's our 2-story high crops, and there's balconies. And you can make this a nice, spacious place that people might want to live in for many, many years, unlike, say, a tiny aluminum can brought from Earth. Zooming in a little bit, so all the solid lines are masonry structures built into the hillside, and then the non-solid are out in the flat area. So kitchen area, dining, multi-purpose. There's the medical. There'd be an alternate emergency medical area elsewhere, labs, common space. By the way, we're getting down to actually, I think that scale is wrong. I believe the total base is about as long as a football field, the length of all the greenhouses. Okay, the private quarters are separated on the far side of the base from the noisy industrial area, and they would be well shielded, but with windows looking out over the valley. So up here is, the furniture wouldn't look like this, but this is the size of a 2-person room. You could have a divider down the middle. Here it shows 2 single-person rooms, hallway, and the main toilet facilities. Okay. Going on to manufacturing, balance of plant is, well, you have the nuclear reactor cores brought from Earth. The balance of plant, you think of rotating machinery generators, but we also use the heat from the nuclear reactor for the manufacturing, making plastics, preheating, when we're extracting ores, metal from ores, etc. So it's important that the nuclear reactors be close to the manufacturing area. Let's see. And here's our gas production and storage areas, like methane and the breathing gases. Okay, so we build up to a crew of 12 people. They enlarge the manufacturing, and they start building a permanent habitat for themselves, where they could live the rest of their lives. Some of them could come home, but we're hoping that the majority of them will stay, literally the rest of their lives. Now, by the time you get up to full production rate, you can build this 12-person base in about 2 years, and we planned that. I mean, you'd have stuff in the pipeline. You wouldn't start with raw material and be finished, be moving in 12 years, but at the rate of 12 persons worth of space every 2 years. So the launch windows are 2 years apart, an additional 12 people can arrive. Actually, maybe a couple might go back to Earth, and 12 plus the replacements would arrive. And you still have this manufacturing area, and you just keep building around the hill. So this is what we call build phase 1, or the hillside base. And hopefully, yes, now 2 years later, you have space for 12 more people. These might be mostly scientists. And then 2 years after that, you have space for 12 more people. These people might be agricultural specialists, they might be scientists, they might be some kind of construction engineers, they might be planning to manufacture basically rovers and portable habitats that you can establish outlying bases. That's to be determined. But basically, we want to keep growing. I didn't mention the way we're paying for this is savings in return flights. About half the cost of a round-trip mission to Mars is the spacecraft to get off the surface, to go from the Mars orbit back to Earth, and either the fuel or the fuel processing. We could literally save half the cost of a round-trip mission if the people aren't planning to come home. Now, the first crew could be able to come home, but by the time you get up to the third and fourth crew, the first crew's been there for 10 years, and we're pretty sure the third crew and the fourth crew can stay there for 10 years if they need to. So we're not planning to have a rescue vehicle ready and waiting to go. And that's how we save the money to pay for the industry. And this is where it leads. People will be planning to spend the rest of their lives as scientists, engineers, or farmers, or miners, or actually operating teleoperated equipment that does the mining. And we think this would be much more cost-effective than round-trip missions. So, going into details, halfway. Are there any questions about Mars? It has about the same, a little more than 24-hour daylight. It's cold, but it's not chilly because the air is thin. Does anybody have a technical question about Mars? Yes?
At the location you have selected, what's the average temperature?
Very cold. It's about what you see here. It rarely gets up to 17 centigrade. It's more like minus 50 centigrade, minus 70. But the air is only 1% as thick. So if you're out in your pressure suit, you actually have a problem of heating, right? You get hot. A tool left out overnight will become cold, though. So it is a serious materials problem, although it's not as bad as on the moon because the air moderates the temperature on Mars. So, a moon in free space and asteroids have a greater temperature swing than Mars does. Okay, resources to build a new home. We are basically homesteading. We are taking the tools to a new world, and we are using the local materials, just like building a log cabin where you only take an axe. So, and by the way, we hope it'll be mostly robotic. Most of the effort will be mostly robotic or teleoperated. Resources we bring from Earth is the people, the temporary living quarters, etc., a lot of dry food. I kind of joke that we should take a 20-year supply of stuff that's hard to grow, maybe certain spices. And so we take enough for the crew that they're planning to use until the greenhouses are up and running. But they have a 20-year supply of spices. And if the greenhouses don't work, there can be some really interesting meals. We bring nuclear reactors from Earth. Power is a problem on Mars. We would also bring additional solar power, but we hope it would be for emergency use and then move to outlying areas later. Mining and manufacturing and refining equipment, I'll get into that. Lots of robots, laptops, etc. Oh, and scavenged. Fuel tanks, big sheets of aluminum scavenged off the spacecraft. Construction staging plan. This is, I'm hoping to revise this more, but we advanced deployment of equipment, get what you can running, such as extracting oxygen from the air. Before people arrive, they deploy the equipment, you know, at least the mining equipment, get it running. And we get up to 8 people and then 12 people. This is a very long time scale, but you can be testing equipment as you go and send replacements or send plans to build replacement parts if they don't work out. I got to rush through this quickly, sorry. Okay, resources you could use from the Martian atmosphere, which is mostly carbon dioxide. You can get carbon dioxide, nitrogen, and argon are your buffer gases. Given either water from the air or hopefully water from permafrost, from a well, you can make methane and hydrogen fuels and long-chain hydrocarbons, plastics. Let me just point out, for a lot of the other plans, a lot of your gases are used to make fuel for your return craft, and we are omitting that need except for emergency evacuation of the first and second crew. Okay. Frank and Gary, feel free to interrupt if you want to clarify. Okay, air separation can be done several ways. One way is you cool it, you freeze out the carbon dioxide, you adsorb out carbon dioxide and water, and you're left with nitrogen, argon, and you can start the process of making fuels using Sabatier reactors and other things. And by the way, as you cool it and freeze out the CO2, you can use that cool CO2 to come back and cool another stage. It's basically a multi-stage refrigeration process interspersed with adsorption. Martian water we hope to get from wells. We hope they can be pre-drilled. Somebody please get a good automated well driller. Okay, we have backups, but main use of water is growing food. Here's our design for a greenhouse. This particular one is earth sheltered and artificially lit. And this is where the greenhouses are in the plan. Okay, but also, nice drawing by Phil Smith inside the greenhouse. Okay, here is an alternate greenhouse that a few of us have been thinking about. One of the problems is what happens if you lose some of your electrical power? We want to minimize the heating and cooling loads. So here's an alternate design where the greenhouse has side windows and mirrors and a curtain, and at night you can close the curtain and basically conserve the heat. And it's sheltered by regolith. It's also very close to a workshop here. So here's the greenhouse, here's the workshop. The workshop acts as an emergency living quarters. By the way, several team members haven't actually drawn this slide. It was made by Frederick just last week. So, so if due to some power failure you can't afford to heat and cool the whole base, you can hole up next to the greenhouse and use convection to stay warm from the sunlight in the greenhouse. And this is a double-wall greenhouse, so you can play games with the pressure between the walls and convection between the walls, have a chimney to adjust the heat. Okay, getting into what else can you do with the atmospheric gases and the water? Well, you can make plastics out of thin air. You can basically make a laptop mouse out of thin air on Mars. From the water, the hydrogen, and the carbon dioxide, you can make methane, ethylene, polyethylene. The other plastics are harder to make, but can be made. Here is a diagram showing an extrusion for making polyethylene material. Think kitchen utensils. Mixing bowls. Think spare parts. Think cases. Think furniture. Okay. Okay. Yeah. So Frank is going to be talking to this slide. You don't have to read it, but there are basically some really long chain hydrocarbons in here that you can make other plastics, polyester. Come back in 1 hour to hear this slide. Oh, I'm sorry. Okay, from the Martian soil. Okay, This upper left here is the average composition of the soil. It is oxides of silicon, iron, aluminum, calcium, etc., with a lot of other traces, including a little sodium and chlorine, which is useful. And you do fairly basic ore processing. It won't be as concentrated as the economical ores on Earth. And you come out with gravel, sand, let's see, somewhere in here is raw material for cement as a byproduct, silicon to go into glass, iron. Where did aluminum go? Anyway, these would be basically, dump trucks, small sifters, crushers. Okay, one of the easier products to make, we believe, will be glass. Fiberglass, glass fibers, glass insulation, glass windows, and mirrors. To make glass, it is slightly analogous to making cotton candy. You find the right proportion of sand, right mixture of sand, you heat it up, you extrude it through a die that has little holes. So here's a picture of a die. You cool the drawn fibers, gather them up, coat them, wind them up. In this case, you can chop them up from glass fibers and also polyester. Polyester is easier to make than epoxy. You can basically wind large tanks. And we would like to wind a tank maybe half the size of this room, half the width of this room and the length of this room. And live in it, basically make things like mobile homes and join them together. You can make glass window panes and mirrors. This is the float process where you pour molten glass and basically float out a glass plate at the cool end of the tank. Steel and aluminum I won't go into, but we have estimated the quantity of materials for all of these, estimated the mass of the equipment needed to bring it from Earth. There's about 4 or 5 PowerPoint presentations on our website that go into details on each of these general areas. Given aluminum or steel plate, it's fairly easy to roll it into a tube and weld it. This doesn't take a big piece of equipment. You don't need equipment this big, you need equipment this big plus some extra stuff around it. By the way, one thing we're thinking, this whole process is redesign Earth's industries to be fit in the back of a pickup truck. What out of Earth's industries is critical to bootstrap Earth's industries? Go back 50, 100 years ago, find out how they did it on a small scale, fit it into a pickup truck, take the pickup truck to Mars, and then make a pickup truck. And it's not rocket science, but it is basically all kinds of engineering. And we are looking for people with experience in basically every area of industry and also non-engineering that can contribute to this. Okay, nuclear power. How are we doing on time? 10? 10:30. Oh, I'm late. Okay, nuclear cores brought from Earth. We did estimate the electrical demands for the different refining and manufacturing and other processes, added them up. We kept adding nuclear reactors during the design phase. Thermal use. The nuclear reactors do produce a lot of heat that is used to preheat the plastics, the ores, the metals in the industrial processes. And basically look at the other presentations on our website. Electrical distribution grid, I'll skip over. We would like to interest students, anybody who has spare time, anybody who's enthusiastic, to work on some area that can be fit into this puzzle. If you want to select existing kitchen equipment that is the right mass to go to Mars, robots, felt and paper. Can somebody design a small tank that can make either felt or paper or pressboard? I'm sure it can be done. It'll be about this big. Don't ask me about explosives when I'm late on time. I get carried away on that. If anybody has connections with a commercial company, could you arrange for donations of the prototype equipment that they used some time ago, the smaller prototype equipment? So, and I got to keep going. We would like to make a full-scale research and outreach center. This would probably be in conjunction with other organizations, commercial companies, and perhaps a museum or university, where we would show a mock-up of a Mars base, and the public, and different parts of it are used for research on how to live on Mars and how to integrate new technologies. But when the researchers are not using a particular area, it would be open to the public. And we're hoping that a significant amount of the building, the construction cost can be from private industry, but the maintenance cost would hopefully be from the ticket sales of the public coming through. Even though this would be billed as a research and outreach center, the real important thing is to change the public mindset so that sometime from now, when somebody is up before Congress saying, "Oh, well, we got to be able, we can't go to Mars because of the gravity, the radiation, the cost of coming back, whatever," somebody in the room will say, "Hey, I saw this Mars base where they were building on Mars and they didn't really come back." So we want to change the public mindset. That's basically the whole purpose of this group, is to figure out how to do it, how to stay on Mars with one of the first missions, and then publicize that. Okay, I think I'm done. Yeah, I'd like to credit several people in the room. Let's see, Gary, Frank, Brian, Martha, Joe and Mark are at the conference but not in the room. And Frederick, who came from Norway thinking he was going to be an intern at a high-tech organization, and he chose this instead. So, actually, so here are various views. Rapid prototyping, that you could redesign equipment back at Earth, send the CAD files, and make the parts on Mars. I'm going to pass around a sign-up sheet and flyers. Oh, and we may have positions for intern and summer jobs over the summer, subject to funding, and if anybody can help us with sponsorship, please say so. And I have hard copies of a lot of the reports up here. I will set them on the back table. So basically, come look at these. I don't think we have time for questions. Is that right? Okay. Questions while we set up. Gary, Gary or Brian, would you pass these around and the sign-up sheet? There is a back.
Yes. What's the current state of knowledge about the existence of water you can drill to at your site or other types, alternative sites here?
Okay. The current state of knowledge for drilling for the water in the site location. We have data showing how much hydrogen it reflects back radiation to spacecraft. So this doesn't tell you how much water there is at a site. It tells you how much water. Well, it tells you how much either that there's a little bit of water in the topsoil or a lot of water deep down. You can't judge the depth too well. But some recent data shows very high percentages of water, especially at northern and southern latitudes away from the equator. Now, there's advantages of being near the equator. We would dearly love to have a robotic driller that can go down, several hundred meters or even a kilometer down and see if there's aquifers. There's some possibility of liquid aquifers due to the pressure, but we can survive by adsorbing and dehumidifying water from the air at greatly increased cost. Or if we had to, we could relocate near a polar cap. By the way, if you go anywhere near the polar caps, you have condensation right before dawn. So the water almost condenses out of the air for you.
Can I add one word to that?
Yes.
Even at the equator, some of our latest scientific research is looking very promising compared to a couple years ago.
Yeah, we're finding more and more water. It's evidence that might be mud flows in recent geologic history. Yes.
Is the diet for these people primarily vegetarian, or is there any scope for animals?
Is the diet primarily vegetarian? I love that subject. What you have to look at is the cost of growing the food per calorie, per unit of protein, vitamin content. So it's basically you say how many square meters of space and how much power does that crop take. Cows are very inefficient. Okay. The reason we have cows here in North America is grass is easy to grow. So yes, it would be primarily vegetarian. However, the waste processing that we were planning to use has a lot of byproduct of duckweed. And in some of these waste processing plants on Earth, they just scoop the duckweed up and then they have to get rid of it before it ferments. So what we want to do is feed it to fish, tilapia or other fish. So
Collecting tilapia recipes.
Yes, we actually are collecting recipes for Mars. So methane broiled, tilapia. I want to add, if anybody thinks they're not an engineer, oh, I can't help with this, come up with a recipe for a pepperoni and cheese pizza that does not rely on pigs or cows. Okay? Now you can make soy milk and you can make soy burgers, but I want to taste a pepperoni pizza, and it can be done. So, but basically primarily vegetarian plus fish. But one other thing, you can stagger the seasons in the greenhouse. So you can have, at least as the greenhouses get larger, you can have something in season frequently from different areas. You can have tropical foods. You can have peaches require frost every winter, and we can freeze part of it. Instead of having a 3-month winter, we can have a 3-week winter and get more productivity out of peach trees. Folks, let me not shortchange Frank. I will be in and out for the next half hour because I have another meeting that I have to go to. We can have more discussion just before noon during what's called future directions. And we have a table at the top of the escalators. Some of us will be there during the lunch break.